right. Hello, everyone. So I'm here to try and tell you a bit of a story on how we at our company Select Data go from what's initially PDF documentation containing clinical information, which usually presents as images, and how we go from that to actual structured, useful information to be used in a series of downstream tasks, which are not that interesting for the audience, at least. So the menu for today, we are going to start on how to actually get the data, which is something that it's kind of overviewed most of the times. Then we're going to go a little bit on named entity recognition, but thankfully Ines already explained, I guess, the nuts and bolts of it, so we don't need to spend too much time on it. Afterwards, we'll dive a little bit into assertion status classification, which is a task which is somewhat specific to the clinical field, and you'll see why. And then we'll touch upon entity resolution / normalization. And before you ask, yes, we are also using LLMs besides the traditional NLP models, and we can discuss a little bit how exactly we are using them. So starting by getting the actual data. At our company, we deal with clinical documentation. We basically are at the intersection between care providers and insurance companies, meaning that we get the data from the agencies that actually provide the care and then help them in structuring their information in order to be submitted for reimbursement purposes. And although this market, it's pretty huge, the data maturity is still pretty low, meaning that although in the home health space in the United States, we see billions being moved around, we also see faxes being moved around. We see printed documents being handwritten on top. We see documentation being scanned and then emailed to third parties. So although there have been some standardization efforts, the flow of the data is still very, very traditional, unfortunately for us. And while the research in OCR is an interestingly old field of research, the innovations haven't quite kept up with the innovations in the rest of the AI and the NLP space. So from an applied perspective, which is from where we're looking at things, we kind of need to take the time to think about two main questions when choosing an approach, when choosing a framework or a given model. First of all, how good are the benchmark results? Meaning, if I'm going to make a bet on developing a feature that requires some model, in this case, is there something out there that tells me how good these different models are in different fields and different industries? And second of all, how easy will it be for me to fine-tune those models, to adapt them, to tweak them, and to exploit them for our specific use case? And these two questions will be kind of horizontal to the rest of the problems that we face. These are not necessarily just focused on OCR, and we'll see how they make sense for the rest of the steps as well. But going into our own decision in our own process, there are plenty of choices for you to make when you want to extract text from images. You have commercial options, you have open source options, you have approaches that focus on traditional machine learning, you have new approaches for focusing on deep learning and leveraging transformers. You have different frameworks on how to leverage these models, both end-to-end frameworks or two-step approaches, as they call it. But in our specific case, we decided to go with something which is this two-step approach, which basically focuses on, first of all, detecting where in the document the text is, and then after those regions are detected, we perform the recognition using a second step or a second model. For the first of these steps, we leverage a framework called CRAFT, which is this character region awareness for text detection, which basically leverages large vision models like BGG16 to act as feature extractors, which then are used to classify different regions of the image as to whether they contain characters or not. And besides the ability to classify the presence of characters, these models are also, or this model, also calculates something called an affinity score, which basically tells us whether a character is close enough to another character so as to make a whole single region or line or word eventually. And this is what allows us to go from this initial document, which presents as an image. This one is not too bad. It's pre-processed, obviously. We remove noise as much as we can. We unskew it as much as we can. We prepare it for craft, which then gives us the regions where we are most likely to find the characters in the image. Then those characters, when they are close enough together, are considered to be a single line, and then we can use those lines to feed them to the next step, which will be the actual text recognition. So in our case, we didn't really tweak we don't really tweak craft, meaning it works pretty well out of the box for our purposes, for most of our documents. We have some annotation efforts, but it works pretty well as is. The idea then is to take these lines of images and feed them to another model, which will take care of actually recognizing the text inside. And as I mentioned, there are multiple options into what model you might want to use. Internally, we are kind of biased towards transformers, which you'll clearly see on the rest of the presentation. And currently, we are leveraging something called TR-OCR, or transformer-based OCR with pre-trained models, which is a model that has been published by Microsoft, which basically combines a visual encoder and a language decoder. The architecture of the model is relatively simple in the sense that what the authors propose is to basically combine some sort of vision transformer. In their case, empirically, they went with BAIT, which takes the image, which in our case is the line of the text that was previously detected. That line is flattened, the patches are fed into the encoder, and the encoded information is passed on to the decoder. The decoder, in this case, again, chosen empirically, has been Roberta, which is a model of the BERT family as well, which then takes that encoded representation of the image and decodes it into language tokens. The advantage of this model, or one of the advantages of this model, is that the annotation structure, or the structure that you need to actually create training data, is pretty simple, in the sense that you can just run craft on a series of images and then just transcribe the text that you are reading in those lines. It has yet another advantage, which is the fact that if you look at the attention layers, or the cross-attention layers between the encoder and the decoder, you can actually see where in the image you have contributions to each of the tokens, which in our case, it's particularly useful because of the feature that we have in the product, which relies on kind of highlighting where the information came from. So having this sort of understanding of what exactly is going on in the generation of each of the tokens is pretty interesting. So now, we got the text, we have the text on our side, no more images. We need to perform the act of actually extracting the information that we need. As Inez has already presented, the whole idea behind name entity recognition is to extract these pieces of information. That makes sense for us in order for them to be either stored or used in other downstream tasks. In our case, we don't deal with logs, we don't deal with IPs or dates, but we are focused on clinical entities, obviously. So in our case, this means that we are especially interested in detecting diagnosis, symptoms, procedures, ADLs, IDLs, etc. And once again, you have a lot of options in terms of architectures to actually perform this NER step. The BERT-based family of models has proven quite useful. Again, as Inez has said, empirically, there are a series of models which have shown that work quite well for a given task. In our case, we have one added advantage, which is in the biomedical domain or the healthcare domain. There are a lot of already heavily pre-trained models that we can leverage for our tasks. So between BERT, Roberta, the Silbert, you can take your pick. And within this domain, you will most likely find something which has been pre-trained for the domain that you like. Again, in our case, we are biased toward these models, and we leverage BERT-based models for this token classification step. And when I say BERT-based, most of the models that we use are actually vanilla BERT. We have some Roberta models, but BERT by itself has performed quite well. So empirically, we are just sticking to it. And how does it work? As I mentioned, we are doing essentially token classification. So what happens is that we have the text that was extracted from the image. This text is further split into sentences, and then these sentences are fed into our model, which will be able to extract these token level embeddings. These token level embeddings are then fed to a simple linear classifier, which will help us distinguish between the classes that are interesting for us. In this case, the labels for each of the entities that we are interested in detecting. So this will allow us to basically step by step start and build our structured representation of what was initially an image. And in this case, we can start by detecting which entities, which information of interest is present in the document. But as I mentioned, in our particular case, we don't want to just detect whether a certain diagnosis is present or a certain symptom is present, because we have one particular type of problem, which is, if you look at those two sentences, you will see that although both diabetes and pain are relevant entities, they have different, what we call assertion status, meaning that in the first case, diabetes is something that is happening for the patient, while in the second case, the patient denies that he has pain. And for, in our case, reimbursement purposes or for clinical summarization or to extract a clinical history, these will be relevant, because if you are trying to build some sort of structured summary, you can't present both entities as having the same level of importance, because one is actually impacting the patient and the other isn't or has before. And this is called generically assertion status classification. And this is essentially a sequence classification problem. So what we have is a sentence where we detect our entity, and then again focusing on these transformer models, what we do is, instead of looking at the token level, we look at the sentence level. So we pull the embeddings of all of the tokens, we wrap the entity of interest around spatial tokens, and then we fine-tune our model in order for it to classify the whole sequence as, in this simpler case, present or absent. So again, taking one little step further and adding a little bit more of information into our structured data that we're extracting from the image, because now, more than just the entity, we know whether this diagnosis has been present or not in the patient, or if it's just a reference to something that he had in the past or the family had. The last step of this sort of overview and higher level recipe is to actually normalize the entities, because unfortunately, in the clinical domain, and I'm sure in other domains as well, multiple users will have multiple ways of referring to the same thing. So in this case, diabetes type 2 or type 2 diabetes are the same thing. And for coding purposes, for clinical coding purposes, they refer to the exact same scenario, meaning that we have to find some way to actually normalize the entities that we have previously extracted and attribute them some sort of standardized and common representation. In our case, we leverage something called the ICD, which is an international classification of diseases, which basically attribute a single identifiable code to each existing diagnosis, which then can be used for interagency communication, for reimbursement submission, etc. So what we are dealing here with, it's a little bit of semantic search. So the way that we do this is essentially by trying to create a vector database of all the entities of interest, for example, the whole ICD vocabulary, along with some synonyms, along with some variations. And then we can just take the embedding vector of each of the entities that we have found, and using your metric of choice or your method of choice, essentially try to do a little bit of retrieval and understand what's the closest match that we have in our database that has an associated code, so that then we can use that code to represent those entities that we found in the text. Meaning that, once again, we take a little step further, and we can add a degree of normalization to the information that we have just extracted, in this case by including a very specific code that will be used to identify these diagnoses. And that will be crucial for, again, in our case, reimbursement purposes. But the logic can, I guess, be applied to a variety of problems. So if I basically had to sum up the, I guess, the three main takeaways behind trying to build like an overarching pipeline such as this one that we are building or have built, I would say that there are basically three main things that you would have to take into account. The first one, which is specific for us, which is we are dealing in an applied setting, meaning although we do some fundamental research, our goal is really to bring value to the product. And so since we want to very quickly have something in production, what we have to do is to accept that there are no perfect models, there are no perfect architectures. However, some of them will be more useful than others for your use case. Furthermore, there are a bunch of benchmarks published out there, some of them academic, some of them open source. And you should really leverage them to try and figure out what are the main top three options for you to start with. The second takeaway would be that regardless of the task that you have at hand, whether it's named entity recognition, assertion status classification, even the OCR, which would be the first step of all, you will almost always need to fine-tune whatever model you are using to your data. Either just fine-tune or actually tweak the model to adapt to your data source. And finally, if you want to fine-tune, you need data, you will need annotations, so you will have to deal with the fact that you will either annotate the data yourself or have someone annotate the data for you, which then brings you a series of not necessarily problems, but preoccupations, such as having correct guidelines to define what's a diagnosis. How do you distinguish a diagnosis from a symptom? How are you sure that the team that's doing the annotations are actually following these guidelines and have a sort of continuous feedback loop in place? And finally, just a brief stint about LLMs, which, of course, as you know, have kind of revolutionized pretty much every NLP task in the close past. And it's the same case for us, meaning that we are slowly trying to bring on board LLM usage, both commercial LLMs like GPT and open source LLMs, specifically Llama, to do a series of tasks for us, or at least to improve a series of tasks for us. The first one, which was super surprising for us, is actually spell checking, which is a pain because if you have dealt with OCR before, you'll know that it's a pretty cool random data generator. And these models, by their very generative nature, are very, very capable of taking something which is noisy and regenerating the text in a format that will be much more fit to answering tasks. We are also leveraging these models for some data pre-annotation to try and cut some costs and time when dealing with our human teams. And of course, as is usual, and which I think is something that's going to be talked about in the next talk, I think, we are also leveraging to do some structure summarization, meaning imagine a patient that has seen a doctor for like 5 times in the past 6 months. We can take those encounters, summarize them, extract the relevant information, and produce a consolidated report that will be easier for either the agencies or the clients to actually understand. And some other secret features that we're developing too. Thank you very much.
Thank you so much, Pedro. Another amazing presentation. I could stay here more 2 hours listening to you. So let's try to be fast and take all the 4 minutes for questions. We have a few ones very interesting. The first one is about the type of documents. If those documents contain table and images, and how do you deal with those type of content, if it's differently or not?
Yeah. So there are a series of extra modules that we kind of can use in this pipeline to actually figure out which pages we will be using to extract the information. We do some sort of document classification or page classification, which most of the times leverage multimodal information, meaning that we've had a lot of success with, for example, Layout LM, which takes both the image representation and the text that we have lifted, and we try to figure out whether it's a page that actually contains diagnostic information or whether it's something that we will have to take into account in another time and place.
What about manuscript text?
For the manuscript part, we are working on handwritten OCR recognition models which rely on actually classifying whether the lines are handwritten or not, meaning that craft is pretty decent at detecting text which has been handwritten too. The thing is that we don't know a priori whether it's handwritten or printed. So we have to have an interim layer here where we actually classify the image as to whether it's handwritten or not. And then we parse it to the respective model, in this case TROCR, which has been fine-tuned for handwritten data or for printed data. Sounds beautiful, in practice doesn't really work.
Okay. Yeah. Another question, have you tested Tesseract for OCR?
Yeah, Tesseract was our original legacy model. It worked pretty well, but for the same experiments, or for experiments that we ran, basically contrasting Tesseract with other options, including TROCR, for the same data, it just kind of started to lag a little bit in terms of performance, so we've kind of dropped it.
Amazing knowledge. What about abbreviations? How do you deal?
Abbreviations are usually included in the training data as regular entities, so we don't do anything special about them.
Okay, next one. For sentence level classification, are you using sentence transformers?
Yeah, we use sentence transformers just because they are more apt at actually dealing with the whole sentence. But we also have some approaches which are simpler, more vanilla, basically just pulling the embeddings of the sentence tokens, and it also works pretty well. So still a toss-up on.
Okay. So last question, and you covered a lot. How different are the challenges that clinical documentation present from other kinds of documentation? I love this one.
Okay, so the first challenge is something which is a little bit strange, which is it's way less sophisticated, meaning as you've seen, we get a lot of documents which are still faxed, emailed, etc. So the source document tends to be super noisy. Then let's say that you have dealt with it. Then as you are dealing with actual text, you have to consider things like dealing with PHI, respecting HIPAA rules, etc. Meaning that unless you have a pretty solid BAA with your clients and are kind of ironclad in terms of privacy, you will probably want to do named entity recognition, for example, but for anonymization purposes, meaning you should be trying to detect names, addresses, social security numbers, etc., but in order to obfuscate them before you either store the data or serve it to other downstream tasks.